filmar, quédate más o menos en la zona.
Vale.
Lo digo en inglés entonces, ¿no? Todo, desde el principio. Estás transmitido en vivo, ¿eh? Te están viendo personas y todo. Okay, let's start. Today's seminar is on Wednesday because Andy, the speaker, is traveling tomorrow, so he cannot do it tomorrow. Thank you, Andy, for giving the seminar on this project, TOT, stellar dating. So Dr. Andrés Moya is doctor by the University of Granada, and then he was working as a postdoc here at the Institute, then at the Observatory of Paris Meudon. Then he turned back to Madrid, to the Centro Astrobiology, and then he was director of the Master of Astronomy and Astrophysics in the International University in Valencia. And currently he is now in a Marie Curie Fellow at the University of Birmingham. He's co-author of more than 80 papers and with more than 2,000 citations. His main subject of research is structure and evolution of stars, astrosismology, and characterization of exoplanetary systems. So, Andy, please,
okay.
It's your.
Thank you very much for all of you for coming here to hear this presentation. The first thing is thank René for the opportunity of giving this talk, and it's a pleasure for me to be here again, because I always feel like this is my house. This is home for me. And it's really special to present you the IAA, my current work at the University of Birmingham. This presentation is about a Marie Curie Fellow that I have for the last 1 year and a half in the University of Birmingham. The project is called TOT. It's devoted to stellar dating. The project has some collaborations with doctors Bill Chaplin, Guy Davis, Andrea Miglio at the University of Birmingham, David Barrado and Centro Astrobiology, Elisa Delgado Mena at Oporto, at CAUP, and Luis Mazarro at UNED in Madrid. Because this project is gathered different knowledge and different techniques from many different places and people. So we need all of them. Well, let's start by the beginning. Why bothering on dating stars? Why we want to date stars? Data star talks about evolution in general. As soon as you want to understand physics related with evolution of life, of planetary systems, it starts themselves, the galaxy structure. To understand all this evolution, the main tool we have is dating stars. Dating stars, we understand exoplanetary system evolution. Dating stars, we can measure if we can see biomarkers or not. Dating stars, we can do galactic archaeology. All these things. So it's related with many different things. A structure of the galaxy, evolution of stars, or biomarkers. These are different. So, for example, this case, I don't know if you have seen this plot. This is the Earth as an exoplanet, and this is the spectra of different biomarkers and evolution with time. And we see that some biomarkers like this one or ozone start being measurable from half of the life of the Earth. So the Earth as an exoplanet has had life for almost all his life, but is measured using our technology just in the last half. So we must know the age of the exoplanetary system to measure the chance we have to see life on them or not. So dating a star is a problem, and is the most difficult stellar characteristic to be measured. Effective temperature, metallicity, log G, mass, radius are easier than the age of the star. This is the most difficult one. In the literature, there are many techniques for doing that. This is a classification done by Soderblom many years ago, and there's different options. The first is, well, fundamental is only the sun. That is, we really know because we have measured we are here and we directly take stones, analyze them, we get the age of the sun with a high accuracy. Semi-fundamental, kinematic traceback, that is, we have a group of stars that have been born together and move. So if we measure the different movements and go back, if all of them are coincident at the same time in the same place, we know the age and of all of them. And nucleocosmochronology. That is, it's like the carbon-14, it's similar. And it's using some radioactive elements, unstable elements, and the ratio between them, between thorium and uranium, I think. And measuring the ratio of the abundance of these elements, you can measure, like with carbon-14, you can measure the age. But these two cases are really rare, really difficult to use. Especially this one, you need really very low metallicity stars, and in a very bright, and you must measure this, the abundances of very difficult elements to do it, and you need some groups with some special situations. So these two are not very useful. Model dependent, that is one of the most used group. Cluster turn off. If you have a cluster, you measure in the HR diagram the turn off elbow, and then you have an estimation of the age. Lithium boundary, the lithium boundary for low mass stars, and asteroseismology. Here you have a lot about asteroseismology, or isochrones fitting. You have a grid of models, you have a position in the chart diagram, you fit a model using Bayesian techniques, etc. So they are very used in the literature, but they are model dependent. So the result depends on the unknown parameters and the numbers you put in the known parameters. Empiricals. This group comes from a single paper of 1972. That is chronology, activity, and lithium depletion. So Smik-Shuk or something like this found that the rotation of the stars, the activity index, and the lithium decrease with age in general. So it can be, the age can be measured using these three indexes. Now geochronology is being under some doubt with some recent findings, so I'm not going to talk, if I don't have time, I'm not going to talk about it because now it's not really useful. Activity has more chances to be used, and lithium depletion, we don't fully understand the physics of lithium depletion. We don't really can link together age lithium depletion. So these three are not really accurate or not really precise. And the statistical ones, chemical clocks and galactic heating. Chemical clocks, these two I'm going to talk in detail during this talk. So I'm not going to explain it now. So we have a number of options. The idea of thought is to gather all of them in a single code. The idea is that for dating a star, if you are a researcher and you have some observations and you want to date the star, you don't need to be a specialist in any of this. You got thought. So you put your data, whatever they are, and then thought select the best techniques for in your case and give you the best date possible with your data. and you don't need to have this at home. So each technique has its own group of stars that can be used for. For example, gyrochronology can be done using the rotational period, and a statistical thing is better for clusters. You measure in clusters the rotation, and you more or less can date the cluster. But some people are using for isolated stars or individual stars, and it's a risk. Okay, stellar activity. You need to have the activity index, the Mount Wilson S or the RHK prime, etc., and can be used for individual stars or clusters. Stellar abundances, you need the abundances, the surface abundances of the stars, can be used for dating individual stars, etc. So each one is suitable for different situations, and it's difficult to find different that can be used for the same star, but sometimes it happens. Okay, so gathering all of them, you more or less cover all the options that you can find. So the main goal of the project, more or less I described them, is to gather all the techniques available, all these things, update some of them, just to offer something new in some cases using empirical relations that I'm going to talk about them now, and to develop this software. So the first step 0 is data-driven. The first thing I've done in thought is to revise the data-driven relation combining general stellar characteristics, that is, empirical relation for estimating stellar masses and radius. Having an estimation of the mass and the radius of the stars is an incredible help for dating. Okay, so the first step is to have some estimation of these values. And for them, I have revised empirical relations. These empirical relations are not from the very beginning. The HR diagram is an empirical relation. It's a relation of temperature luminosity in main sequence. It's a temperature luminosity relation. And it's not linear, but almost linear. So in first order is a linear empirical relation. So from this point, there has been a number of different empirical relations relating observables. Okay, and one of the most known is the mass luminosity relation. Many people use it. In the literature, there are some of them. Luminosity or radius as a function of mass in the Mirka and Karaman. Torres et al. Is one of the most used relation where the logarithm of the mass of the radius is a function of effective temperature, log G and metallicity. Ecker, luminosity as a function of the mass. Benedict, mass as a function of the magnitude for very low mass stars. Ecker again, luminosity and radius and effective temperature as a function of the mass, etc. So there is a number of relations in the literature for obtaining masses as a function of observable or the other way around. What we have done is to gather a data sample, the biggest data sample possible. All these works has one thing in common. For doing these relations, you need accurate, precise effective temperature, log G, masses, and radius. And these two are difficult to obtain. What is the best way for knowing masses and radii? Eclipsing binaries, detached eclipsing binaries. So all of them have been constructed using a set of detached eclipsing binaries. What we have done is taking the advantage that astroseismology has now provided a large set of precise masses and radius, and we can add to the data sampling. So we have gathered more than 700 main sequence stars from many different catalogs, and combining masses and radii coming from eclipsing binary, astroseismology, and a small amount from interferometry. So we wanted to to mix different techniques in order to balance the bias of the different techniques. Okay, and covering from B to M, but mainly around AFJK stars, where asteroseismology and eclipsing binaries have been more studied. The asteroseismology is more around FJKs, eclipsing binary cover a larger range of a day chart diagram and some just anecdotal interferometric determination. With all this, we have a large data set with precise masses, radio, effective temperature, luminosity, metallicity, gravity, and density. And with all of this, we can use big data techniques, machine learning techniques for estimating new empirical relations. The first thing we have done is just to analyze the correlation of the independent variables. That is, we are going to do mass as a function of effective temperature, luminosity, We assume that these are the independent variables. And we are going to do mass as a function of this and radius as a function of this. So the first thing we have done is to test the correlation of this one in order not to avoid using the same two highly correlated independent variables in the same relation. We have to avoid this. And with that, we find that most of them are not correlated except two cases. This one are expected case. In the case, gravity and density are highly correlated. Yes, there is one over radius of difference. But we don't know the radius, in fact. But beside that, and knowing the radius, we can, if you have one of these two, you can have the other. Data says. And luminosity and density has some correlation, okay? But there's some information here, so we have to keep them. With all of this, we have tested all the options. Mass as a function of any combination of one variable, two variables, three variables, four variables, five variables. And radius, again. And we have, this is really small, I did it on purpose. We have published 38 combinations, 38 new relations. Some of them are similar to those in the literature. 38 new relations combining mass as a function of the effective temperature, radius as a function of the luminosity and the gravity, mass as a function of the effective temperature and the metallicity, etc. All of them with an adjusted R square larger in general than 0.9. That means that the relation describes the 90% of the variation of the data. So it takes this, explain at least the 90% or more of the variation of the data, except in 4 cases that are larger of 0.85 in any case. The accuracy we have found is that in almost all cases, except 3 cases, the accuracy is better than 10%. And the precision, just taking into account the uncertainty in the coefficients, are better than 7.5%. So the statistics are really good. And so you can use this relation for estimating masses and radius with uncertainty of 10%, 15%. That for an empirical thing, just to have an idea of where we are really good. And as a bonus track, we have a new log G log density relation with a R square at 0.99. So knowing one, you know the other. But we have also used the advantage of having a large data set, and we have trained a random forest. So we have used machine learning things. That's for the estimation. So we have trained a random forest regression, and we have found that using the random forest, we obtain accuracies of 4.7 in the case of the mass and 3.3 in the case of the radius. So using machine learning is, and it's really fast. And you can, on the fly, add new data to your data set, and every time you train a new random forest, you have more information, and you don't have to reobtain all the relations. It's more easier for a general code to use the random forest than the relations. So this was the first thing. This has to be already published, and with this base we have moved we have developed a first code for the estimation of these masses and radius. Is the first step in the big code. So with this code, as soon as you have effective temperature or any of these 5 values, you just have to put it here, choose the relation you want to use, go, and you obtain the mass and the radius. So you don't need to program it. And more or less, this is the idea of TOT, finally, to offer this kind of tools. It's a package that can be launched in R or Python, and the installation from scratch is really fast, and it's a browser front end. So as soon as you run it, it opens a browser, and you just have to fill, push the button, and go. It's really easy. So we have moved now to stellar dating itself. The first thing we have done is to revise chemical clocks. What is a chemical clock? What's the idea? The idea is the following. Different stars, different masses evolve at different timelines. So the more massive, the faster its evolution. And when it explodes, it creates new chemicals, like new elements. And the different masses create, at the end, different group of elements. So the massive the star, the faster its evolution, and creates this yellow group. It's called the alpha elements, in particular. Some of them are the alpha elements. On the other hand, the lowest the mass, the slower the evolution, and it creates other elements, the S elements, and another physics for the generation of these elements. So we have two different time scales, creating different group of elements. So if we assume that at the moment of a star's birth, it takes the elements of this moment in the galaxy, so the galaxy is chemical homogeneous, and with the elements of this time related to these explosions, and assuming that these abundances, the surface abundances, is the same as that at the origin. It cannot change it. Assuming these two things, that is, assuming that the surface abundances we see now are the surface abundancy at the moment of the birth, then we can date it. Well, this is what I'm going to present is a paper recently accepted. So, for example, let's see. These are different alpha elements with time. Okay, this is gigayears. The alpha elements, as alpha elements related to iron. Okay, so at the very beginning, just at the first years, the most massive stars start exploding, and they pollute the galaxy with alpha elements. So the galaxy is enriched of alpha element. Every star birth at that moment has more alpha element than others. With time, new elements appears, and the relation alpha-iron decrease. And this is what we see. That, for example, magnesium, iron are larger, there are more magnesium than iron in the older stars, and with time, this ratio decreases. More iron appears, and the ratio decreases. Okay, so these alpha elements more or less has this shape with age. On the other hand, the S elements is the other way around. they appear the last, because they are originated with the low massive stars that start exploding at the end. So at the very beginning there are almost nothing, and with the invested time they appear. This relation is really bad. It's a little bit, the slope is a little bit down, okay, but they are the only elements with a negative slope. The idea is the following now. Okay, what if I combine a positive slope element with a negative slope element? So I can increase the relation. I can increase the relation. So if I make the ratio of anticorrelated with H element and I correlated H with element, for example, an S element over an alpha element, then we can have a chemical clock. Something with a slope, with a relation with H that is larger. It's big. With many spread, I mean, it's not a great stellar dating technique, but it gives you information. Okay? So these are the chemical clocks 1D relation, that is H equal a chemical clock. And this relation is quite good. We have analyzed it with the data of Elisa Delgado Mena, around almost 400 stars with very accurate elements, 20 elements, and good ages. And we have found that okay, these are the relations with a R square of 0.80, 0.60, so it's not bad. Okay, but it has an uncertainty of almost 2 gigayears. But what if, okay, the idea now is, okay, there is some spread here that can be due to physical things. Which physical things? One of the assumptions is that in the surface is unaltered with time, and it's not true. With time, stellar evolution changed surface abundances a little bit. So what if we introduce into these relations the position in the chart diagram? Different position can have also an impact. So we have introduced, for example, 2D relations. We have added the mass. Now we have with empirical relation estimation of the mass, or the effective temperature, or the metallicity, plus a chemical clock. And now the relation is better. And we have also tested a 3D relation. Effective temperature, metallicity, and chemical clock. And it's the best option. We arrived to R squares close to 0.9, and 90% of the variances. So it's a very good thing. And we don't improve, so it's the top limit. We cannot explain more than that. We have added more dimensions, and nothing changed. We have changed the dimension, the elements we use, nothing changed. So the 3D dimension using the position in the chart diagram, that is two elements plus a chemical clock, is the best working here. And well, it goes. So this is the dating using chemical clocks. Galactic heating. What is that? With time, the galaxy is evolving, it's moving. And it introduce some interaction between the stars, and they disperse. They start moving at different positions with different velocities, and these velocities change with time. So the idea is measuring the kinematics of the stars in the galaxy. We can more or less see and know the age of the stars. If it's really dispersed and moving fast, it's older. The youngest, the quietest. Okay? And more or less it works, but it's a statistical thing. Here I show three in elliptical coordinates, the 3 coordinates. This is the age, and this is the sigma, the dispersion in velocity. And we see how the dispersion in velocity increase with time. But it's a statistical thing. So the oldest more velocity. The youngest, less dispersion. So what we see is if we measure the kinematics of a star and we see that is almost has a low velocity in any coordinate, we don't know anything. It can be young or old. But if suddenly we have one coordinate with a large velocity, it start pointing to an older star. So what we have done is to fit this relation, this increasing with time of the sigma, and use it in a Bayesian way. I mean, to estimate the percentage, the probability of an age for a given kinematics. Where is the sigma, which the element that's having the dependence with age? Okay, and doing it. This is the worst technique in the literature, but it gives some information sometimes. So it's worth to use it because the kinematics values now are really easy to obtain. We have large data samples of many stars with these values measured. So it's almost for free to have an estimation using this technique. Third technique, isochronous asteroseismology models. As soon as we have a position in the chart diagram and maybe pulsations, we can go to models and grid of models and fit it. We have gathered two different algorithms for doing that. A Stepter is done in R with a grid with some parameters, and an algorithm of maximum likelihood, and a SPINS. There is a SP of AIMS, is another package done in Python with another grid with other physics and MCMC Bayesian fitting, so other technique. And we combine both. And we also use the empirical mass, the estimation of the empirical mass as a posterior for a fine tune of the age. That is, we obtain, with this, we have effective temperature, log G, metallicity, etc. We obtain a probability density of mass, radius, and ages. With a new estimation of the mass coming from empirical relations, we can re-estimate the probability distribution of the age, because we now know the real mass. Okay, so this is a quite complex statistic from a statistical point of view technique using radiation sampling, using a metropolis Hastings, blah blah blah. But it works quite well with the bad point of being model dependent. And the last one I have studied up to now is activity. In the literature there are many activity relations of the age as a function of activity indexes. Okay, this is the original, well, the most used one of 2008 of Mamayek and Hillebrand, and two new relations coming from Diego Lorenzo Oliveira. And in this case, I just used them with the correction coming from using harps in this case instead of von Wilson, etc. Doing some corrections for you using this. Okay, this is what we have now in thought. What are we doing? First step, the sun. Do we estimate the age of the sun correctly, for example? The sun as a star. From the sun we know the effective temperature, we know everything. So I have put it on these techniques, and using chemical clocks. This says that the age of the sun is 5 gigayears plus minus 1. A Stepter 5 plus minus 2, SPINS 6 it goes. Plus minus 3, it doesn't know anything. Kinematics is really bad, 4 plus minus 3. Activity 5 plus minus 1. this is the distribution of these different techniques. The probability distribution. More or less all give a similar age, a prediction of the, except kinematics. Kinematics says that this one. So the probability distribution says that, maybe it's quite young, but I don't really know. Well, no problem. I have the others. And altogether provide a final estimation of 4.96 plus minus 7, 0.7. We think is the real value within errors. And here we see that the blue one is the estimated, the errors, this is the final error bar, and the red one is the real one. And this is the estimation of the different techniques. So the idea of thought is, as soon as I have different options, combine them from a statistical point of view. Just don't use only one. If I have more available, take it, use it, add it using probabilistic techniques, and your final result will be better. Another case, one star in M67. Is a cluster that we know the age quite well. And this star has, we know the effective temperature, log G, metallicity, all the elements, and the kinematics. So we almost have everything except activity. Here, chemical clocks 4.7 plus minus 1, acceptor for 4.2 plus minus 2, kinematics plus minus 3, okay, the kinematics always like that. But all combined, 4.5 plus minus 1. The real one is there. The real one with errors overlaps. Okay, and if you see the distribution, the probability distribution, again, kinematics more or less. Well, say it's young, but maybe also in the real zone, except chemical clocks, and altogether more or less, this is the real one. And it provides a quite good estimation combining all of them. And this is thought. And the final goal will be to gather gyrochronology, and with the group of all these plus gyrochronology will give a broad options for almost all the cases, and put all these in a computational tool that you don't need to understand all these things. As soon as you have effective temperature, log G, blah, 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 and the position and the kinematics, you just put it on top, and it makes the work for you. And that's the idea. So this is the project, and thank you very much. And I have a project web page if you want more details, and just visit us.
Thank you, Andy, for this talk. Any questions? I have one. In the last two slides, you put the age. In the case of the sun, you say a real one. The real is determined by the meteorites, I think, with this error.
Yes.
So in the other case, how you determine the real one?
This is a cluster. So we have the turn off. So in the HR diagram, when you have a cluster, there is a moment where the stars leave the main sequence and evolves to subgiants. At this, it depends on the mass.
That's why the error is.
Yeah. So it's larger because in my opinion, it's small. So this turn off, depending on the case, but in general, it cannot be better of 1 giga. But some people are more optimistic than that.
The question that I made to all the stellar people that I know, which is the 0 point of the life of the star? Because in the real time, the real 0 point of the sun is determined by the meteorites, and we know how, because of the condensation of some particles. So, but this is not true with the other star.
Yeah, there is so well determined, because the real life of the star can be where the hydrogen burning starts. Okay, so it condenses, and then the nuclear reaction starts. Okay, but what does it mean? Because it's not a turn-on, turn-off thing. So it's little by little. So there is some uncertainty in where to put this zero H main sequence. But the difference between one option and the other is not larger than a few megayears. 10 megayears, tens of megayears. So at this range of gigayears, finally this uncertainty in this definition is completely within errors. The youngest your age, the larger the impact of this thing. But as soon as you think that it's impossible to go down to 10 megayears in years, you don't care because it's within errors.
Okay.
Hi, Andy. Thank you for your nice talk. And I was wondering, do you have to give as an input every parameter? I mean, what's the minimum if you don't have, for example, the log G, or do you have to, for a good estimation, what is the minimum parameters that you have to give?
But the minimum you need to have an estimation, and the easiest one is the standard HR diagram thing. Effective temperature, effective temperature, log G, or luminosity and metallicity. With these three, you can have an estimation, because it's the minimum inputs for the model-dependent tools. Except use temperature, log G, metallicity, and spins, effective temperature, luminosity, and metallicity. This is why spin has not provided anything, because I don't have the luminosity. But this is the minimum. Or these three values, the kinematics. But the kinematics gives you almost nothing. It's something that only gives you a small amount of additional information, but don't trust an age coming only from kinematics. So the best thing is having at least three of effective temperature, log G, all luminosity and metallicity. And then the models fit, the algorithm fit the model, and you have something. Then as you have activity, you have additional information. If you have at least one chemical clock, you don't need all. With only one, you have some information, at least a small piece of information, then you add more things. If you have more chemical clocks, the better.
What's the role of rotation in all of this? Because you don't include any variable depending on the rotation, no?
No, because gyrochronology is not under doubt. Okay, so rotation is almost there in everything except, and one thing I haven't said is that sorry, one of the better thing of this thing is that all these techniques are physically independent, quote, physically independent. That is, the kinematics, so how the velocity of the stars, has nothing to do with the surfactant abundances. It's another physical thing. So we can easily combine them from a statistical point of view. Okay, has nothing to do with activity. Activity comes from rotation. So, for example, activity is really linked with rotation. The surface abundances has some relation with rotation, but in the sense favoring our assumptions. That is, rotation tends to avoid, to stop diffusion. So the only thing, one of the things that can change the surface abundances with age is diffusion, but rotation tends to stop it. So the larger the rotation, the larger the chance of these surface abundances to be the original one, because it's more or less frozen. So rotation is almost there, but not explicitly there, except with the activity that is a measure of rotation, more or less.
Thank you, Andy, for this very nice talk. I have just a curiosity. In terms of the kinematic distance, do you think it's much affected by stellar migration across the disk? Or can that be used in this sense, in the opposite sense, just to...
In fact, it's affected by many different things, and not all related with age. Migration has something to do with age in the sense that it's an evolutionary thing that with time it migrates, time is there. But this is the weakest part. That in the general sense, yes, the larger the time is in the galaxy, they start rotating with the galaxy, the larger the dispersion, more or less. And this is the only idea. And you see that in a statistical sense, more or less it follows. It's something like the larger the time, the larger the dispersion. But you cannot go further than that. So
it's just a statistical sense.
Because I think for galaxy formation models or disk galaxy formation models, it would be interesting to see whether the migration hypothesis that had been used in the models and where exactly in the disk is this migration farther, or that would be interesting for me to see whether this In
this particular case, there is no models here. They are just data. The data have gathered the velocities of the 400 stars of the sample we have with the chemical clocks for having all together. And if you put all this together, you see this, that there is an increase with age in the data. No models there. And the best one is this one, that you have almost a linear increase. So this is the set X. So the movement in the set X is more related with age than the movement in the horizontal coordinates. Yeah.
And that's a curiosity. You didn't mention that you don't use cosmochronology. The nuclear how is this? How is this? Is disregarded now? Is being used?
I have only seen two stars dated using this, because you need a really special situation. You need a really bright star, very low metallicity, with a very low metallicity. Because as soon as you have more lines, the lines you need for thorium and uranium, you don't see them. So you need a population 3 star, hydrogen and helium, and a little bit of other things, and really bright. You need to see a little the line of thorium and uranium, and then do it. And I think that only 2 or 3 have been done in the literature. So it's there. It's a technique, but it's really hard to use.
Does the performance of the code depend something on spectral type that you are using for individual stars? Or does the performance of the code depend on spectral type, or it's better for solar-like stars and worse for, I don't know, giants or very low mass stars? Or
on the case. For example, activity, most of the technique are fine-tuned for solar-like, FGKs. That's it. That's life. But for example, and for me, it's my favorite one. Is the chemical clocks are valid for everyone, because only depends on when it was burned. It was born. So no more things. So it could work from N to O's or more, because that has nothing to do with the physics of the star, because it's just the elements at that moment gather, and in the surface I see them and point to a moment. But activity depends on the physics of the star, so it's more optimized for FGKs. Model fitting depends on your grid. If you have a grid and a good position, you have a good position and a good grid at the moment, at that position you know it. So it depends. This is what I show at the here. Different techniques are suitable for different groups of stars and different situations. So the most general ones are chemical clocks, stellar abundances. Kinematics is independent of the star, but is a bad technique. And the rest are for FGKs. These two are FGKs, but stellar activity can be used for M stars too. Yeah, you can use it at least below the saturated regime. You can more or less have an estimation of the age also for M's, and the electrons depends on the model grid depends.
Questions? Okay. Thanks again, the speaker.